All right, so I see we've started the event. Are we recording? Okay,
We should be recording right now.
recording
Yes.
too? Okay, fabulous. And are you going to stick around to read off questions out of the chat, or do I need to check on the chat periodically?
I will stick around for the entirety of the
Okay.
meeting, and I will also be reading the questions in chat. Yes.
Okay, thank you so much. Just checking. Just checking. All right. I think all those go. Whoopsies. All right, so we are starting off exam 3 review for general chemistry. So we're going to start off with some general announcements before we get into some content. So real quick rundown, just a reminder for the exam rooms. I don't know if y'all remember because this was all before spring break. So I've just got the room assignments posted. Those will also go out in emails just to remind all of y'all. But we did have a change from exam 1 to exam 2. So we are sticking with this set that was from exam 2. So small group of people got affected because we swapped rooms a little bit, but those are posted. Make sure that those are available. Similarly, speaking of things that are posted, hanging out in the 701 section. So hanging out on the course homepage under the exam information, the potentially useful info sheet and periodic table, exam 3 is posted. So if you were curious as to what equations we were adding, what was going to be different about the equation sheet this time around, that is all up. So that Henderson-Hasselbalch equation is there in that bottom left-hand corner. So just so you know, that is posted and up there. And we'll be using that today a little bit as we go back and forth. But I know it's always a question of like which equations are given, what's on there, what's not on there. And so I just thought I'd mention that that did get posted actually on Friday, but by the time I realized it, I'd already taught class. So as usual, do go ahead and start to drop questions in the chat. I, of course, have some to help out with that. Prepared from my class, but whatever you guys want to ask, I'm happy to talk about. So content, what is this exam over? This also got posted in the 701 section, and I updated it with end of chapter questions just this morning. So chapter 17, this says 17.6 through 17.10 in 17.12. For the record, this is also things like weak acids and weak bases, calculating pH. So there was stuff that we did back before spring break. The week before spring break is on this exam 3. So we are going back in time. It seems like a long time ago because we are actually starting with, if you just have a weak base and a concentration, what's the pH? So all of that stuff is in there. So that's there. For the end of chapter questions for 17, my recommendation, I'm just going to say all of them. This is because, by the way, I know for chapter 17, some of that was on exam 2. So some people are like, but what about specifically for this exam? The thing is, y'all still need to know how to go in between Ka and Kb. Y'all still need to be able to recognize conjugate acids and bases. So a lot of y'all still need to have memorized your strong acids and your strong bases. So even though there are some things that we specifically asked on exam 2 that we won't specifically ask exactly that question on exam 3, you need all of that information. So you still need to be able to recognize conjugate acids and bases, even though on exam 2, we had a question that was something like, if this is your acid, please pick the conjugate base out of a set. We won't do that now. Now we're going to do things like, you have these two things, tell me what the pH is, and you need to recognize that they're a conjugate acid base pairs of each other, and that therefore it's a buffer. So I'm just going to say that all those questions are valid. Chapter 18, there are some things that we exclude specifically So into chapter questions, though, I'm just recommending all the recommended ones that are in that PDF file, because we did cover all of 18 that we're going to cover for this course. We did. Chapter 15, I did go ahead and make a specific list, questions 1, 2, 4, 8 through 11, 14, 20, and 22. Because we are only covering a small section of chapter 15. We'll do the remainder of 15 on exam 4. So, and believe it or not, I actually really like where we cut chapter 15, but you'll find out why I really like where we cut chapter 15 when we do the exam 4 review. Because I frankly think that all of the stuff that we leave for 15 actually goes really well with the rest of the stuff we do in the rest of the semester. So those did get posted. I basically just left those in the 701 section under the announcements tab, but they're also here. So got a couple different spots for those recommended questions. I'm gonna unhighlight those because that pink is a little bit of a dark highlight color. So as far as questions, I'm gonna go ahead and grab a couple of the kind of general questions I got from my class. I do have more questions from them. There's some more in there, but I'm going to go ahead and start with just some of the general questions that I got. And we can talk about more specifics, or we'll see what you guys wanted to talk about specifically out of the chat. But first, while we're waiting for questions to come in from the chat, I'm going to grab these. So one of them is asking about good study methods. And I always think that this is a valid question. So, and it says specifically here, but nothing is working. So in case you're curious, I did reach out to this student specifically. One of the challenges though, and this is mostly just to add to the validity of this statement, because I feel it, I get it, is whenever you're studying for an exam, and this one is no different, you're trying to balance concepts and calculations. And the tricky part about that is sometimes those things are mushed together. This exam coming up, a lot of that information is mushed together. Sometimes it's just a concept question. Sometimes it's just a calculation question. But oftentimes they're mushed together. And so one of the challenges is to essentially figure out where you're having the most confusion. So this is one where one of the things that I like to offer as a thing to potentially start with is to either do pure tutoring in the library or the chemistry clinic, and then sit down and try some of those end of chapter problems. And the reason why I like you guys to try to like do those problems, but in a space where you can get help immediately when you get stuck, is to then ask yourself, if you're having problems with those end of chapter problems, is it because the concept doesn't seem clear, or is it because you're stuck on a calculation? Where is the problem? And sometimes the answer is you don't know, because you're like, it just doesn't seem like it makes any sense to me at all. So that's also why I like suggesting that folks basically try to work problems on their own, but work it with help nearby. Because sometimes there are things that you can totally do, and there are other things that you can do with assistance, and there's other things that you're just like, do they really think I can do this? It's always a spectrum, and everybody's different. So that's one of the things I like to recommend to try to figure out what to do. Because to be honest, as far as different studying methods, everybody is different, and oftentimes the method you need depends on the material. So for example, for this stuff coming up, especially for exam 3, practice, because being able to look at a problem, figure out what to do, and get it done in a relatively short period of time is going to be a challenge. And so having practice with those and putting pencil to paper and actually working those is going to be really useful. Any other ways you recommend studying other than end of chapter questions in last year's exams? So I got 2 things. So one, last year's exam, I actually really like, especially this year, because one of the questions I got asked a couple times was, what are the questions going to look like? It seems like we've been doing titrations forever. is that all that's on this exam? No, there's lots of stuff on this exam. Last year's exam, we basically covered the same content. So the challenge there is that it doesn't have the same authors, and we usually write 30 to 32 questions, and y'all only see 28 to 30 of them. So there's always questions that we write that you never get to see. So keep that in mind, because there's usually some topic that we thought was really good, but we were like, oh, we have these other questions. We got to throw one off. I guess we're testing this one. So that does always happen. But as far as instructor wise, we wrote questions over a certain block of material, and that block of material was the same this year as it was last year. Again, I don't know what we threw off that we did right because it's been too long, but that will definitely help. The other thing that I will actually recommend, there's two more things as far as study aids that I'd recommend. One of these is ALEC. If you don't know why it was assigned, ask. Assigned for a reason. So all the things that we assigned in ALEX are in there for a reason. If there's anything in ALEX that you're like, I don't know why this is here, ask, because I promise you we assigned it for a reason. Then the other thing is, don't forget things like workshops. You can also look for older exams. This comes with a caveat. But the thing that I like is somehow to have basically questions out of order. Questions out of order. Because the thing is, when you have an ALEX question, it's got a bar at the top and it tells you what the topic is. When you're looking at end of chapter questions, they're broken down by chapter. And a lot of times they're actually broken down by topic as well, because it'll say things like section 17.6. And here are some questions over that information. So workshops are usually where things get shuffled a little bit. And also sometimes older exams. Now, older exams come with a big caveat, which is we used to test on different material. We used to have different grade. We used to have different places where we cut the material. And this didn't happen to us this year, but we sometimes lost days due to ice or winter weather. So depending on what year it was, depends on what's on that exam, which is the reason why I'm super excited about the 2024 exam, because that's actually super helpful. Other exams just kind of depend. So, but they can at least help with, what is this question asking? What is this going on? Is there anything in specific I should drill in my mind? Couple things. Strong acids, strong bases. You have to have those memorized. We are still going to use those. And then as far as like drill in my mind, I would also have the notion that if you have a strong species, so a strong acid or a strong base, the first thing that has to do is react. What I mean by that, so I don't know how y'all's classes have been talking about them, but if you, for example, have 0.1 molar, and gosh, no, just go with it. And something like 30 milliliters sodium hydroxide, and you are adding that to 0.2 molar, and we'll go with 20 milliliters HCl, and the question is, what is the pH? Then when you do this, the thing to recognize is this is a strong base. This second thing, HCl, is a strong acid. They're being added together. That means the very first thing you have to do is react things. I've been using BCA tables. So I've been using things that look like this. So we could consider this to be a titration question. And then I have 0.1 times 30 milliliters, something like 3 times 10 to the negative 3, 220, 2 times 10 to the negative 3. These are in moles, by the way. So the first thing you do is react in moles. In my class, I've been referring to these as BCA tables. BCA to stand for before, change, and after. And the thing is that these are all in moles. Those ice tables that we still need to know how to do, are in concentration units, are in molarity, but these are in moles. So I'm using the molarity times the times the volume to get any of those values. Then, so this idea of if you have a strong species, the first thing you have to do is go to moles and react the thing together. That is something that I would actually recommend drilling into your head, because one of the questions I've gotten a lot is like, how do I know what to do? And one of the things that you can know to do is if you have a strong thing, one of the memorized strong acids, one of the memorized strong bases, you should know that if you have that, you're going to have to react it. It's got to react. You have to get rid of it because it's not going to be just the final thing hanging out in solution. Since I've talked about strong acids and strong bases, let me go ahead and put up, please be here, yay. Let me go ahead and put those up real quick. So here's my strong acids. There are 7 of them. 3 of them, HCl, HBr, and HI, are all together on the periodic table. The other set you basically have to have memorized. So however you like to memorize these is up to you. Your strong bases, I do mostly have the strong bases on the periodic table. So most of these are alkali metals. 5 of them are. The other 3 are alkali earth metals. So strong acids, strong bases, you still need to have those memorized. But if you see one of those in a problem, read the rest of the question, but I can almost promise you it's going to be because it's being added to something else, whether it's being added to a different strong thing, or it's being added to a weak thing, whether it's being added to a buffer, but whatever that strong thing is needs to go away if it can't. Maybe it's the thing that's left over. I don't know. But you have to figure out what's going on with the strong thing. Because I went ahead and started a calculation problem, I'm going to finish this calculation problem. After this calculation problem, I'll take questions from the chat. But I put up a BCA table, so I'm going to finish this. So the whole idea with the BCA table too is somewhere in the after time, something should be 0. Something here, something in the reactants should be 0. This is a reaction. Things are reacting together. Since something is reacting together, the thing that's going to go to 0 is going to be the smaller number. So I have 3 times 10 to the negative 3, and I've got 2 times 10 to the negative 3. 2 is smaller. So this is the thing that goes away. So this is going to be my change. So essentially, we do treat these as minus x, technically plus x. Water is just a pure liquid. So I mean, technically, I am making more water. That water, however, is not going to affect the pH. And then what I have left over is I have 1 times 10 to the negative 3 moles of hydroxide. I have no protons. I got rid of all of those. This question asks for pH. When we go to look at pH, first of all, pH is dealing with protons, and these brackets mean concentration. But I don't have protons. I also don't have any concentration. So I know it's concentration, by the way, because of the brackets. Those brackets mean molarity. I don't have molarity, I have moles. I also don't have protons, I have hydroxide. So I got 2 different issues right now. So I'm going to fix the molarity, I'm going to fix the unit problem first. So I have 1 times 10 to the negative 3 moles of hydroxide. If I could divide that by liters, I could have molarity. I would still have the molarity of hydroxide, but I at least have molarity. So I need a final volume. We are just going to assume that you can add these together. This is for, the main reason is we are assuming that these are dilute enough solutions that we are assuming it's just like adding water together. So we're basically assuming that since these are aqueous solutions, that they are close enough to being mostly water that we're just going to add those volumes together. So I'm going to add 30 and 20 milliliters. So that is 50 milliliters, and there's 1,000 milliliters in 1 liter, gets me 0.05 liters. So I can at least get myself a number in molarity. Woohoo! But that's hydroxide. I don't want hydroxide. But what I am going to go ahead and do is I'm just going to calculate the POH, because that is going to get me closer to what I'm looking for. So my POH is the negative log of 0.02. My POH is therefore 1.7. The question asks for pH. So since I want pH, that's where I'm going to rely on the whole 14 shenanigans. And that, I believe, let me check potentially useful information. Okay, so we do have, let me highlight that. So I do have pKw is equal to pH plus POH. That equation is on here. What I was using is, since we have memorized that Kw is 1 times 10 to the negative 14, that does mean that pKw is equal to 14. You can find that by taking the negative log of Kw. My goal is to still solve for pH. The thing to double check. So as you might have noticed, even I was like, that was a lot of math. We'll just take a deep breath. The other thing to double check before you're like, yes, this is definitely the correct answer. We're going to go back to the BCA table, because the number that I just solved for tells me that this is basic. This is a pH greater than 7. So the last thing I actually want to do, even as I just took a big sigh of relief, I must be finished. I actually want to say, all right, that pH is greater than 7. What did my BCA table say? So I'm going to scroll back up and take a look. And when I'm looking at my BCA table, what I'm looking for now that I've solved for pH is I just want to see what I had left over. And this said I had hydroxide left over. So out of the two things I started with, a base and an acid, my BCA table said, hey, that's a base. When I finally solved for pH, my pH matches what I knew at the end of my BCA table. BCA table said you reacted away all of the acid. The base is what was left over. My pH, when I was done, also says you have a pH greater than 7. That's a base. So I want to try to make sure that those things match, because they should match. The thing that your BCA table tells you you have left over should match your pH at the end. That was trying to answer a question I had prepared for, which is, what should you have drilled into your head, or what should you know? So in addition to the strong acids and strong bases, one of the things I recommend is essentially, if you have strong things, strong acids, strong bases, you should think, I'm probably going to react those together. So I'm going to go to moles and react them together. One of the things I would recommend. Okay. So let's go ahead and see how we're doing. Are there questions from the chat?
Yes, we have 2 questions. The first question is, can you do a titration problem where it starts with a weak base in the beaker? And can you do it at the equivalence point and after the equivalence point?
Okay, great.
The second question is, can you explain the Lewis acid and Lewis bases and how to identify them?
Absolutely. Okay. So we'll go ahead and answer the titration question first. Think about this for just a minute. Okay. So first of all, I need a weak base, which means I need a KB value. I don't know about Shell. I'm kind of tired of sodium hydroxide. I'm definitely tired of sodium hydroxide. I'm kind of tired of ammonia. So I meant to grab. I'll just make it up. Just gonna grab. I will make up a base, so we can do something different. So we're gonna go ahead and say we'll go ahead and calculate the pH. pH after gosh 0. I'll make this larger in just a minute. We'll use HBr because I haven't used HBr in a while. Weak base KB equals something kind of small, but a number I haven't seen in a little while, 4.5 times 10 to the negative 9. Oh, it looks great. Okay, so I'm going to make this larger so you guys can actually read it. And I will also now access my superscripts. Okay. So it does just say weak base instead of saying a particular weak base, so that we can practice. We are going to go ahead and assume that the weak base is this thing, so that we can practice writing conjugate acids and bases. I don't promise that this is actually correct for its KB, but we are going to practice. So I have two different things going together. So because I have a strong acid, here is my strong acid. And I have a weak base, granted it said so, but we're going to use this structure. I'm going to react them together first. So I'm going to have HBr plus this thing, ethylamine. And that is going to give me CH3 and H3 plus, technically, and Br minus. The other thing I'm going to do though is, so essentially this is a strong acid, so I really could have written this like this. And I should be putting aqueous by absolutely everything, but I'm not right now, because that will make this giving me even more things to write out. One thing that you might notice is, so since that HBr is a strong acid, I can go ahead and write it as H plus and Br minus, even in the reactants, because that's actually what I have. What I should then be able to see is I have that bromide ion on both sides of my reaction in exactly the same way. Because of that, I can actually rewrite this as a net ionic equation. So that I can essentially not worry about the bromines. So that way I'm not thinking about that bromide concentration. It's essentially hanging out in the beginning. It's going to hang out in the end, and I just don't care about it. It's a spectator ion. It goes away. So I can think about my net ionic equation instead. Now I'm going to worry about moles because I have a strong species reacting with a weak species. So I'm going to care about moles. So I'm going to take 100 milliliters and multiply it times the 0.2 molar. So 0.1 liters times 0.2 molar to give me 0.02 moles. And in a perfect world, to get that both times. So my strong acid has 0.02 moles, and my weak base, even though it's different numbers, 0.05 liters times 0.4 molar also gets me 0.02 moles. Beginning of the problem, I don't have any of that conjugate species. But what you might notice is this is my conjugate acid, and I am going to keep track of this. It is an acid by itself, so I need to keep in mind what it is, because it could affect the pH. So I need to keep track of it to see. So that is my before. Then I need my change and my after. In my after, one of my reactants goes to 0. So since one reactant is 0, I need to subtract the smaller number. I look at my 0.02 on both my reactants. It's the same. So that is actually how I know I have the equivalence point, is I have no reactants left over. I'm going to go ahead and add to my conjugate species. But one reactant is 0, but that's not what really happened. Both reactants. That is how I know I'm at the equivalence point. So that BCA table gives you a lot of information. It's part of the reason why I like them a lot. I'm trying to emphasize that more this semester. That end of the BCA table actually tells you a lot of what's going to happen. I know that there's more stuff to do because the question is, what is the pH? And we're not done yet. But this right now tells you a lot about what's happening. So one, I know I'm at the equivalence point because I'm out of acid and I'm out of the weak base. So I ran out of the strong acid and I ran out of the weak base. I ran out of both of those things. I don't have either reactant. They're gone. I'm at the equivalence point. So that tells me that information. Then either because I know I'm at the equivalence point and I started with the weak base, or because I can look at my BCA table and the thing that I do have left over is a conjugate acid, I know from the BCA table that my pH when I'm done should be less than 7. So my final pH should be an acidic pH. I'm at the BCA table. The only thing I have left is acid. If the only thing I have left is acid, gotta be a pH lower than 7. So I know that already. Now, like I mentioned, I could also know that just from the fact that it's an equivalence point. Every equivalence point for each of the 3 types of titrations has an expected pH that's unique. And it's because of what you know should be true at the equivalence point. The one that we're doing right now is strong acid, weak base. Strong acid, weak base, you get rid of all of the strong acid, you get rid of all of the weak base. What you have left is the conjugate acid. Therefore, your pH is less than 7. Doesn't matter what weak base it is. This is what happens at every equivalence point for weak bases, which is all your weak base is gone. You've made conjugate acid. pH. So now we are to solving a pH for a weak acid problem. This is now essentially a chapter 17 problem, which is given a weak acid, what's the pH? So what I need to be able to do is take this weak acid, CH3, NH3 plus, and consider its equilibrium. Which means I'm going to be using a Ka value. So I need a Ka value for starters, but also Ka expressions are all in concentration. I'm using those brackets again. If I'm going to use Ka, I'm using molarity. I don't have molarity right now, so I've got to fix that too. So in order to solve this problem, I need 2 things. I need a Ka value, and I also need concentration. So doesn't actually matter which one I solve for first. I guess we'll solve for concentration first, because as I scroll back up to my ice table, I see this lovely 0.02, but that is in moles. So I have 0.02 moles. What's my volume? I have 100 milliliters and 50 milliliters. So I have a new volume, which is 150 milliliters. Again, we're going to assume that the concentrations are low enough that we're just like adding water together. So I have 0.02 moles divided by 150 or 0.15 liters. So I have a new molarity of 0.133 molar. So that is how I'm going to start this table. It's been a while since we did one of these, but this is an ice table. So this is my initial, then my change, and then equilibrium. So I do at least now have an initial concentration in molarity. That started. Next up, I need a Ka value. I'm going to scroll back to my problem and see what the problem gave me. The problem gave me a Kb value. How interesting. I have a Kb value. Well, that's because I had a weak base. So it gave me the Kb value of a weak base. I don't have the weak base anymore. I have an acid. That equilibrium has a proton in it. So I need a Ka value because of the proton. I have a Kb value, 4.5 10 to the negative 9. Great. So I'm going to use this. Kw is equal to Ka times Kb. So I have Kw memorized. It's not on the potentially useful information page. So I have that memorized. And my Kb value is 4.5 times 10 to the negative 9, according to my problem. Now we're just going to cross our fingers that the math works, because so I get a Ka value of 2.22 times 10 to the negative 6. Now I can solve my problem, because at least now I have the pieces. So my Ka value up here, 2.22 times 10 to the negative 6. I'm going to finish my ice table. We're assuming that there's no protons, that there's no conjugate base, even though I know that we started with that in the BCA table. We reacted it all away. So yes, now we're using equilibrium to essentially get some of it back. Ice table, negative x, positive x, where the zeros go. This is 0.133 minus x. This is x. This is x. So there's my ice table. Sorry, it's a little crooked. Here's my Ka expression. So this is equal to x squared divided by 0.133 minus x. Gosh, I would really like to use the approximation method, and I would love to assume that this x here is 0. How do we do that? We go ahead and compare 400 times the Ka compared to the initial concentration. 400 times my Ka value is 8.89 times 10 to the negative 4, and that is smaller than my initial concentration of 1.33. So we can use the approximation. That's supposed to say approximation. So we are assuming that anytime we would add or subtract x, thinking back to exam 2 style stuff, this was this idea that if you had someone who made a lot of money, so we'll say, we haven't used Mark Zuckerberg, the person who runs Facebook, Meta, whatever the heck it's called. If Mark Zuckerberg drops $1 out of his pocket, technically he lost $1, but his net worth is so much that we don't recalculate all of his money because it's just $1, and $1 in comparison to all of the money that he has doesn't matter. That's essentially the same thing that we're doing here. We're assuming that the change is so small that if you added or subtracted such a tiny, tiny number, it wouldn't make a difference. So any x added or subtracted, we are assuming is 0. That's the approximation method. So we're solving for x. 2.22 times 10 to the negative 6 is equal to x squared. That's squared. Sorry, my handwriting is so bad. I have my tablet. I'm just having bad handwriting today. So this is 2.956 is equal times 10 to the negative. Don't randomly drop your exponents, y'all. I need those. Times 10 to the negative 7 is equal to x squared, and then we square root both sides. So then I get x is equal to 5.44 times 10 to the negative 4th. So I have a value for x. It's in concentration. My goal was to solve for pH. So since my goal is to solve for pH, I need to know if this x is hydroxide or proton concentration. It's one of those two. I've been using Kas and Kbs, but by the time I do all of this math, I don't always remember which one I've done. So I'm going to go back to my table, and that x is my proton concentration. Great. That x is the proton concentration. That's why I was using a Ka value. Great. So because that's what the number is, we're going to use pH. Sorry, I looked at it for a minute. I was like, what do I do now? Like, oh, I plug it in my calculator. 3.26. And again, we take that nice deep breath. We solved. But again, we got to scroll back to that BCA table. Now, in this case, because we had to say it a couple times, I'm pretty confident that our BCA table predicted an acid, but I will scroll back because this is an acidic pH. So I am going to scroll back through all of our lovely mathematics. That's an ice table. That's a BCA table. We did. We said it should be less than 7, and that's what we have. Yay! So I'm going to take a quick minute here. One of the other questions that I got asked from my class is I got asked about how do I know when I need to subtract from 14? How do I know if I need to do the subtraction from 14 or not? I'm trying to answer that question through some of these examples. So if you look back at the video, we did have to subtract from 14 on the first problem that I did that involved a strong acid and a strong base, because I had base left over and I had POH and I wanted pH. Here, I'm not using the subtraction from 14 because I wanted pH and I already had pH. So the way you know, do I need to subtract from 14 or not, is by double checking. Do I have protons, H plus? Do I have hydroxide, OH minus? So if I have protons and I'm solving for pH, I'm good to go. If I have hydroxide and OH minus, then I've solved for POH and I'm not ready. That's not the same thing. So the way I know whether or not I'm subtracting from 14 is by keeping track of what chemical species I have. Which means for those of y'all that are big on writing down as few things as possible, you got to keep track some way, somehow, of what you've got. Because a lot of the like, do I need to subtract from 14 or not? Some of that is also keeping track of, do I expect there to be a acid or a base at the end? Do I expect my pH to be high or low? That'll also help with that subtract from 14 idea. Okay, another example with acid-base titrations. I'm going to keep that same AB because why not? Maybe I'll go down here, paste it. But I need different amounts. And actually, we're going to change a couple of things about this problem just for funsies. We're going to change the molarity because changing the molarity is fun. We're also going to change this Kb value because I want a different problem. I want different numbers because that way it'll also be clearer that it's a different problem. So yes, I did just play with numbers a little bit, but that's what we're doing. So slightly different problem, but still dealing with weak bases. We'll make this HNO3. We'll make this a different strong acid just for fun. I understand that for some of y'all it's not fun, but I'm also trying to demonstrate how we make problems look different. So sometimes the problem doesn't seem to be that different, or sometimes the problem looks really similar, but is a lot different. And from the last problem, I really did just change one number, I changed the KB value, I changed the concentration, and I changed what the strong acid was for fun. But something you'll notice, this is still a strong acid. So even though I changed which one it was, that's still a strong acid. This still says that it's a weak base. I could really use a different weak base though. Let's make this C2H6 NH. That's a weak base. I don't know if that's the correct KB, but this is a different weak base. That's a true statement. Still got that nitrogen on the end. So I have a strong acid. Since I have a strong species, strong needs BCA table, need to react. So that's what I'm going to do. So I'm just going to go ahead and write the net ionic equation to start off with. I did a demonstration of that earlier, but I'm just going to go ahead and write the net ionic. So get rid of that nitrate anion essentially. Plus C2H6 NH. This is reacting. So this is going to make C2H6 NH2 plus. This is a BCA table. So I need everything to be in moles. Everything needs to be in moles. Moles, moles, moles. So therefore I'm going to take 0.1 liters times 0.3. So that should get me 0.03 moles and 0.05 times 0.02. So times 0.4, 0.02 moles. It's a BCA table, that's 0. So somewhere in my after, something here, I need a reactant at 0 when I'm done. So therefore I'm going to subtract the smaller number. Subtracting the smaller number here is this 0.02. So that goes to 0. And so I get to add 0.02 here. So I have 0.02 here, and I have 0.03 here. So therefore I'm going to have some of this left over. So I'm at the end of my BCA table. I have 2 things left over. I have acid, strong acid, and I have weak acid. I have both. Now I'm going to go ahead and tell you this. So I have acid left over, acids only. So I expect my pH to be less than 7. Now that strong acid is going to dominate what we do. I only actually need to calculate the strong acid. I know y'all are going to ask me why. So I'm just going to demonstrate why. So first of all, I'm going to solve the problem and get a final answer. And then I'll show you why I knew that that works like that. So because I have a strong species, because I have a strong acid, left over, I'm just going to use pH equals negative log of my proton concentration. I do need molarity, however. So I need to scroll back up here. I've got 100 milliliters plus 50 milliliters, and that 0.01. So that's going to be negative log of my 0.01 divided by 0.15. So that's taking my moles, and that's taking my new volume, because I do have to have molarity. I realize my handwriting is not great today. So again, those brackets mean molarity, so I have to have molarity. So this is the negative log of 0.0667. So that is So my final pH, my final answer, if this was a multiple choice problem, I would be all finished now. Looks like this. Now, again, if this is a multiple choice question, I'm done. I've finished. But I know the question is, but at the BCA table, I just totally ignored the weak acid. I did. I totally ignored the weak acid. So I'm just going to go ahead and do the ice table and show you why I did that. Conceptually, I will also explain that weak acid with its teeny tiny little Ka value makes so small an amount of H plus that it's not going to contribute to the pH. It's going to round away. It's not even going to enter into that calculation. But I know some of you either don't believe me or you're still worried. So I'm just going to go ahead and do the math and show you, because that's going to ultimately save me time. But again, if this is a multiple choice problem, I'm not doing that work because it doesn't change the final answer. So we're basically doing the same problem that we did before. I have moles right now, but I am headed into needing molarity. C2H6 NH2 plus is in equilibrium with the weak base plus the proton concentration. I have 0.02 moles divided by 0.15 liters. Is that the same? There it is. Oh, yay. Sorry, I did not do that on purpose. This makes me very happy. So this is actually the, oh, but I changed the Ka value. Ah, darn it. So anyway, I at least know what the concentration is. So I am basically going to speed run this ice table. If you're not familiar with the term speed running, that just means I'm going to try to do it really, really fast. I need a Ka value because I have H plus. So if I look for my Ka value, I'm looking to take my Kw 1 times 10 to the negative 14 and divide it by Kb. 1 times to the negative 14. I changed the Kb value. Darn it. But I hadn't changed the Kb value. Spread it out. 1.33 times 10 to the negative 7. So therefore, I have a Ka value of 1.33 times 10 to the negative 7 is equal to x squared divided by 1, 0. I want to erase. This is the part where I get a little spoiled. The Wacom tablet that I have in my office is not as nice as the one in lecture hall. So therefore, times 0.133. So 1.77 times 10 to the negative 8 is equal to x squared. I am using the x as small approximation, so that x there is 0. And square root it, I get x is equal to 1.33 times 10 to the negative 4th, or 0.123133 molar. So H plus. So this is the contribution that my weak acid makes. My weak acid contributes 0.000133 molar. So what I'm going to do is I'm going to add my molarities together because essentially it's all H plus. So I had H plus from the strong species, 0.0667. And I also had H plus from the weak species, 0.123133. And I'm going to just add those together. 0.166833. And now I'm going to take the negative log of that. .0668333. log. I get a pH equal to 1.18. So I did an ice table. I had to go back to molarity, and I had to add things together to get the answer I got like 10 minutes ago. So I did that because you don't have to. The weak species, the weak species, the weak species does not contribute to bother calculating. So I actually have another analogy for this. I don't know if you've ever baked anything with small children before. Not like you've had like a 2-year-old like niece or nephew or sibling or cousin or somebody, and you're like gonna make cookies or you're gonna make some sort of like baked good, and the 2-year-old really wants to help, and so you put the 2-year-old in the kitchen, and you give them the wooden spoon and you give them the bowl, and like you hold the bowl and you're like, now stir, and that little 2-year-old like does this for a minute, and they just kind of go back and forth with the spoon. It's adorable. It's a lovely like bonding experience. It gives you lots of warm fuzzies inside. That 2-year-old does not actually help make that baked good. They don't. Um, they're not really contributing to the process. So that's what I think of when I think of you have a strong acid and a weak acid, both in solution together, give me the pH. You really only have to contribute that strong acid. That's the only calculation you have to do, because that weak species just doesn't have enough protons to really make it worth your while. You get the same answer. So I have been talking for about a half an hour. So that means, even though I haven't answered both questions that were asked yet, I'm going to return and ask for questions out of the chat to see where we are. So are there any new questions out of the chat?
We have 3 new questions.
Great.
So our first question is, can you go over common ions and pH in relation with KSP?
Okay.
The second question is, can you do an acid-base problem that incorporates percent ionization in the problem?
Excellent.
Our third
Next.
question is, how did you immediately know how to do an ICE table after the BCA table for the first weak base strong acid problem?
Excellent. Fabulous. Okay. Cool. Anything else for right now?
Nope, those are the only 3 questions so far, new.
Okay. Thanks. Okay. Um, so since there's a question about one of the things we've already done, let me go ahead and address that one first. So I have it labeled here as number 5. So I'm going to go ahead and scroll back. Also, thank you to the person in the chat who called that out as being from the first question, from the first weak base problem. You said it correctly in the chat. I really appreciate the fact that you reminded me which of the questions you were referring back to. So thank you for doing that. That really helps a lot. So we were looking at this question where we had asking about the pH, we had a strong acid, we had a weak base, we did a BCA table, and this point here where we had stuff at the BCA table is where I made a decision about what to do. So actually, to think through that, let me actually talk about my flow chart for titrations. Yeah, let's do that for a minute. Hold on, because this will actually answer that question. So when I think about titrations, this is my mental flow chart. And I didn't even put this in my, I kind of put this in my notes, but then I made a better version of it in office hours, and I don't know if I'm gonna have time to go back and fix it, y'all. So titrations, there are 3 kinds of titrations. You have strong acid, strong base. You have strong base, weak acid. You have strong acid, weak base. So those are my 3 titrations. Like it or not, those are my 3 sets. So 1, 2, 3. 3 sets. No matter what, I do the same thing each time. So I use that BCA table to react in moles. So my first step is the same no matter what I'm doing. So it does not matter which one of those things I have. I am using a BCA table to react in moles as my very first step, no matter which of 3 titrations I have. My first step is identical because, like we've mentioned, you have a strong species in each of these 3 types of titration problems. Since I have a strong species, the first thing I'm going to do is react in moles. So that's the first thing I do. But then after that, there are actually, for each type of titration, there are certain things that I'm going to look for. So I'm going to try to keep these color coded. So if I have a strong acid, strong base, there's basically 3 things I can have. I either have strong acid left over, I have strong base left over, or I have neither. And my pH is equal to 7. That's a strong acid, strong base titration. You can do, and frankly, for strong acid, strong base titrations, those are the only options you can ever have. It's not just pertinent to this course. I don't care. Strong acid, strong base titrations, those in the real world in this class doesn't matter. Those are your only 3 options, period. End of story. For the purposes of this class, strong base, weak acid, I'm going to do these in blue. You could have your give a buffer. We haven't done one of those yet, but you could have a buffer left over. You could be at the equivalence point, which is you have no strong base, no weak acid. If you're at that equivalence point, that means that your pH automatically, all you have left over is a weak base. Your pH is greater than 7. End of story. That's what you have to have. Or the last one, you could have the strong base left over. Realistically, these are the 3 scenarios we're going to leave y'all with. You either have both, you either still have weak acid in solution, but you've made some weak base. So you actually have a buffer situation set up. You're at the equivalence point, in which case you've gotten rid of all the strong base, all the weak acid. All you have left is your weak species. This situation, this number 2, where you're at the equivalence point, this is the part where you have to do an ice table if you're solving for pH, because the only thing you have left is 1 weak species. You can't use the Henderson-Hasselbalch equation. You can't use a buffer if you only have 1 weak species, or you have the strong base left over, that last option. Last setup, strong acid, weak base. I want you to see how similar these things are. Buffer. The equivalence point. No strong acid. It's all gone. No weak base. It's all gone. So therefore your pH has to be less than 7. It's an ice table. Or 3, you have strong acid left over. So we've done 2 and 3 for a weak base strong acid titration. But do look for those weak species, how similar that list is. Buffer, equivalence point, the strong thing is left over. I mostly make them 2 different lists because that pH changes. So sometimes it's a little easier in my mind to say, I realize that mathematically those 2 lists are going to be really similar, but let me go ahead and point out that my pH will actually be different depending on what those look like. There we go. Get it all on one page. So that's my general flow chart for titrations. I have 3 kinds of titrations. No matter what, I do use a BCA table to react in moles. Then after that, I'm looking to see what I have left over. And my BCA table tells me what I have left over. So, and then I essentially only have 3 options, but the 3 options depend on what I started with. So this is the other reason that after my BCA table, I knew I was headed for an ice table, is because I didn't have any of my reactants left over, and so all I had was one thing. I'm going to scroll back up to look at that question, because one of the other things I want to point out for this stuff is I also want to point out one more thing with it, which is why I didn't use the Henderson-Hasselbalch equation. So one of the other questions that the person in the chat might have been asking is why ice and not, let's call it the HH equation, but I mean the Henderson-Hasselbalch equation, which is on the potentially useful information page. This equation here is for buffers. In order for something to be called a buffer, I have to have roughly equal amounts of my weak acid and its conjugate base. So in order to use the Henderson-Hasselbalch equation, I have to have roughly equal amounts of weak acid and its conjugate base. So when I took a look at my BCA table and it said, by the way, you don't have any strong acid, cool. You don't have any weak base. All you have left is weak acid. That also tells me I don't get to use Henderson-Hasselbalch because I've essentially reacted away all of the weak base. So I don't have a buffer. It's just not there. I have so much weak acid and so little weak base that this is not a buffer and I can't use that equation. Now I think I've answered that question. Now I will consider this question answered. So anytime anybody asks me about KF, I refer them back to the things we are testing on and the things we are not testing on. And I know I didn't talk about it a whole lot in the very beginning, but out of chapter 18, we are excluding the part in 18.5 that covers complex ion formation. And that is where KF is. So no KF. None. 0. So that is the thing with KF. So to the person that asked about common ion, I'm basically going to ask back, what was it about common ion you were interested in? Because common ion does show up a couple of different times. I'm happy to talk about it, but I'd like to know which way you meant, because no KF. KF is not a thing. We're not doing complex ion formation. So I'm gonna put a little question mark that maybe I finished this question, but maybe not. So if I didn't answer that question, go ahead and put it back in the chat, and you can definitely blame me. But I'm gonna say there's no KF, there's no complex ion formation to deal with. I might have answered your question, but I don't know. We'll see. Let me go ahead and throw up the stuff about Lewis acids and bases, and then I'll do a percent ionization. Let me take a small break from dealing with type calculations. Do I read my chapter 5? My 7? Nope. Darn it. I need my chapter 17 notes. Oh wait, but I'm in OneNote. I have my notes. 17. And I want. So the reason why I'm flipping back to my own notes is because I made new slides for Lewis acids and bases, because I get asked, how are we going to recognize them? How could we do this? What is going on here? And I therefore, I'm a little lazy. I'm just like, I would like to grab the lists I already made. Bases. Okay, so before I talk about this, first of all, when we talk about Lewis acids and Bronsted acids, so when we say Bronsted, frankly, when we talk about acids at all, Bronsted acid, we're always talking about protons. So we're like, HCl gives away a proton. It's an acid. When we talk about Lewis acids, we are making a broader definition. So my Bronsted acids are all Lewis acids. So every single one of my Bronsted acids is a Lewis acid. If you can identify it as a Bronsted acid, then it is a Lewis acid, period. End of story. But Lewis acids are just going to include more things that we may or may not have considered to be acids before. So there are going to be additional things that are also acids that we didn't really think of as acids before. The Lewis acid definition is broader. It incorporates more things. But your strong acids are still acids, even under the Lewis definition, because it's a broader definition. The Lewis acid definition is all about electrons. So the Lewis acid definition is about accepting electrons. Notice that my Lewis definition involves something that's negative, and it's about accepting. My Bronsted definition was about something positive, and it was about donating. So you do essentially see those definitions flipped. But that's also why they should go together. The thing that has a positive charge can also accept a negative charge. So some ways to recognize Lewis acids. My first one says acids from previous definitions. All the strong acids are acids, all the weak acids are acids. So don't lose that. Metals with a positive charge. Sodium, aluminum, things with positive charges. Usually Lewis acids. Usually neutral metals. That's why I've got copper on there. Iron, just neutral stuff. Compounds in general with a positive charge. Honestly, this one's difficult for me to give you an example that's not already on this list, but I put it on there just in case. And I've got draw the structure last. So The thing with draw the structure is I always think about this as a last resort. So to me, I've got these essentially in order of how I would recommend you look for a Lewis acid. Basically, can you recognize it from something you already have seen before? Is it a metal with a positive charge? Is it a metal? Does it have a positive charge? And then your last resort is drawing the darn thing. Because honestly, we are kind of likely to draw it for you if you really need that, just because we know that this is a time-intensive exam. So we usually draw them for you if we can. But depending on what you're looking at, drawing a Lewis structure might be helpful. So those are my ways to recognize Lewis acids. My Lewis bases are going to look similar, but be about bases. Just commit to drink some water. My Lewis bases is shorter, in part because metals are usually acids. So I don't have anything about metals under Lewis bases because the metals are usually not bases. So the strong bases are still bases, the weak bases are bases, compounds with a negative charge, draw the structure. So those are my general things for dealing with Lewis acids and bases, especially because usually you're looking at things that are very different from what you usually see. Dealing with Lewis and dealing with electrons looks a lot different, but you're looking for things. Charges will help a lot if you can, because since Lewis is dealing with electrons, things that are negative have extra electrons. A Lewis base, you're looking for something that can donate electrons. So negative things can do that better. So hopefully that helps with Lewis acids and Lewis bases. Oh, so I'm going to scroll all the way back up. Haha. So believe it or not, I did titration problems. I did one at the equivalence point. I did one after the equivalence point. I did Lewis acids and bases. I had to identify. I should probably actually grab a reaction then. I was like, I'm done. Oh, maybe not. 17. Do I have some ones? So this is, let me make this bigger. Bigger. This is out of Alex, by the way, if you can't tell. So this is an Alex question. So I don't feel bad to use the Alex question. And it's got something highlighted, and basically the original Alex question said, in each row, check the boxes that apply to the highlighted reactant. So thinking about what I've said before, nickel, I'm looking for things that are potentially metals. If I'm looking for Lewis stuff, I'll just go ahead and copy this over. Where is my periodic table? There you are. So nickel is right here. So it is in that D block elements. So nickel is a metal, so it is likely to be a Lewis acid. So when I'm looking at, oh, not that, this. So when I'm looking at nickel, I'm likely to say, hey, by the way, that's a Lewis acid. Now, that one is a bit more straightforward because it's on the list that we were talking about. Do you have a metal? Yes. Cool. That's probably your acid. The thing is that it would be lovely then, because then if that's the acid, this should be the Lewis base. Seeing that this is the Lewis base is a bit more difficult. This is where drawing would actually come in handy. This is the Lewis base. And even though it looks kind of weird, what you can hopefully see on here is you've got those lovely lone pairs on either side. Those lovely lone pairs are what makes it a Lewis base. I will point out that this problem asked about the nickel. That's the thing that's in red. And that nickel is easier to identify. because it's a metal. So keep that in mind. While yes, you can definitely identify both pieces, sometimes one of them is easier to identify than the other. So you might just go with the thing that's easier. I'm going to come, actually, no, I will talk about this one. This one, I have to admit, is not my favorite thing. It's also less likely to be an exam question. This is neither, and I will show you how this one works. So this is looking at, this is a drawing one. This is probably the other reason I don't like it as an exam question, because you basically have to draw stuff. Yuck, draw stuff. So this is thinking about, here are my two things, and then I make a new thing. So those are my two reactants, and then I make a product, and my new product looks like this. The thing is that when we talk about donating or accepting electrons, part of the thing is I should be seeing something where all of the electrons just come from that thing. But when I break apart H2, I basically get a hydrogen with an electron twice. And then I break apart my bromines, and I get bromines basically with 7 electrons all around them. And essentially what's happening here is each of my atoms brings 1 electron to the party, and they just share. So my hydrogen brings 1, my bromine brings 1, and they're like, hello, we are going to form a covalent bond. Yay! I bring 1 electron, and you bring 1 electron. And there's no donation going on. They're just sharing. Isn't it pretty? So neither donate, neither accept, they just share. So neither one of these is an acid or a base. They just share. I will say this, but I know it's not helpful for most of you. But for those of you that it is helpful for, this reaction with the hydrogen and the bromine is a redox reaction. And because it's a redox reaction, it's not an acid-base reaction. That's actually the way that I do this, is because I am more familiar with redox reactions. I just look at it, and a redox reaction is not an acid-base reaction. And that's the way I actually do that one. So, hello. But that's neither. This one, what you might notice is this one is actually kind of a classic acid-base reaction. Here's something with an H in front of it. Here is something that does not have has some protons, but it goes from neutral to a positive charge. And then I'm left with this negative species. So this is kind of a classic acid-base. So the thing that accepted a proton is also the thing that donated electrons. So that thing is a base, no matter which way you slice it. I can go ahead and draw it out and show you where this happens. So basically, this really is talking about an H plus with no electrons. And then this is connecting with my C2H5 and essentially these electrons are going to connect to that proton. So it's both of those electrons are being donated into the covalent bond to make with that hydrogen. So that's where that comes from. So you can still look at it as a Lewis, even though when you just look at the reaction itself, you can probably identify that by Bronsted. So that, again, once you can identify it as a Bronsted acid or base, it's also the same thing in Lewis, just as a broader perspective. Okay, so we talked about Lewis acids and bases and how to identify them in different ways. Yay! I will also say that in general, we usually want you guys to identify things. We don't usually do the neither thing. So I've got one more question that I have not addressed yet, but I've also been talking for about a half an hour. So I'm going to do that same thing again and ask for questions out of the chat just to kind of see where we are. So are there any new questions out of the chat?
Yeah, see, we have one new question. To clarify the earlier question number 3, it was talking about KSP, not KFP. This is the question about, can you go over common ions and pH in relation with KSP, not KFP? This is question number 3 for you, I believe.
I guess I'm not hearing that correctly. What is the difference?
The letter S versus F. Like S as in Shaggy.
Oh, thank you.
Mm-hmm. And you do have one more new question, which is, can you explain the buffer capacity?
Okay, great. Okay, fabulous. Okay, KSP, that makes sense. I'm so sorry. I absolutely heard KF and was like, formations. No, KSP, that makes sense. Okay, got it. I should probably get my hearing checked, but that's a summer problem. That's not a now problem. In the meantime, I'll just ask for clarification. So thank you for clarifying. Okay, common ion effect and KSP. So common ion effect and KSP. There are, we're gonna start off with the classic version of this, which is to talk about magnesium hydroxide. So first of all, when we are dealing with KSP, one of the things that's happening is just like when we do Ka and Kb, we essentially have a known thing on the left, thing on the right. So in KSP, the solid is your reactant, the aqueous species are your products, and the higher your value of KSP, the more soluble your compounds are. But when we then talk about common ion, what we usually want to talk about, there's two basic things to talk about, is general predictiveness, is just predicting if solubility increases or decreases, and then common ion calculations. So I like to start off with the magnesium example because it's a bit more straightforward. So because sometimes we like to do this with pH, which was mentioned. This makes so much more sense now. So if I have this particular reaction and I tell you that you're in a pH of 9 or a pH of 3, and I ask you which one is it more soluble, which pH is magnesium hydroxide more soluble, and you have an acidic pH and you have a basic pH, which one is more soluble, the acidic one or the basic one? We are looking at the common ion effect. The basic one, the pH of 9, gives more hydroxide, gives more OH. So I already have hydroxide here. So if I increase the amount of that hydroxide, that's going to shift back towards my solid. It's going to shift back towards my magnesium hydroxide. And I essentially am then going to have less of my products made because it's shifting back towards the right. We can actually see this in a calculation. I'll do that in just a minute. The other one is to think about my acidic pH. So again, so if I've got a basic pH, I've got more hydroxide. More hydroxide means I'm going to make less products overall, and it's going to go back towards my reactants. A pH of 3, on the other hand, does something a little bit different, and I want a little bit more space. So here's my lovely magnesium hydroxide. If I then put in H+, so again, I'm thinking about my pH equal to 3, that's an acidic pH. As an acidic pH, I'm going to have a bunch of protons. those protons will actually still react with that hydroxide. I can get H plus plus my OH minus, and that'll make water. So in that case, because I'm reacting with the hydroxide, I expect my hydroxide to go away as it's reacting with the protons, and that's going to drag this equilibrium to the right, which will make it more soluble. So I would expect magnesium hydroxide to be more soluble in acid and less soluble in base. More soluble in acid, less soluble in base. I mentioned we could do one of these as a calculation. Technically, we can do them both as calculations. You might notice my voice being not happy about both of them. So we often do this one as a prediction, because as a prediction, you can go either direction by thinking about what other compounds you could possibly make. And does that either match exactly, and therefore you go back the way you came in the case of the hydroxide, or do you make something brand new and you're going to proceed to make more products? So you can talk about it being more soluble or less soluble. That oftentimes is more beneficial unless we want you to just do a calculation where the answer is less soluble. So I would actually like the actual KSP for magnesium hydroxide. Darn it, I wish I'd made myself a little table. So I'm going to grab that real quick. So while I am grabbing the actual KSP value, I'm going to mention the reason why we would not ask you guys to do a calculation where it was more soluble. That's essentially because while y'all are perfectly capable of doing it, it's kind of long. And since it's a bit long, you guys already have titrations to deal with. So basically, we are more likely to ask you to do a calculation where it's more straightforward. Asking you to do a calculation where it's more soluble would be a two-part calculation, would need a BCA table. And BCA tables and precipitation reactions, we are just not going to ask you about. We're just not. So what I'm going to do is I'm going to do magnesium hydroxide. And we're going to do this basically twice. So we're going to do this as a neutral pH. So since this is a solid, I don't care about it. I start off with none of these. I have plus X, I have plus 2X, I have X, I have 2X. My KSP value, which I'm looking up in a table, I just had it, magnesium hydroxide. On the exam, they are all in the question, is equal to X times 2X all squared. So I can solve for my molar solubility. 5.6 times 10 to the negative 12 is equal to 4x cubed. So notice that I did have to square the number 2 as well as my x. So this is also x times x. 4x squared. My AirPods died. That makes me sad. But now that both of them are dead, maybe I'll hear better. So basically, I can go ahead and solve for x. This is what's known as molar solubility, because I'm going to get an answer in molarity. So the other reason I wanted to show this off was to remind y'all to figure out how on your calculators you want to do a cube root. Personally, I just raise everything to the 1/3 power. That is what I usually do because it works better for me personally. But that's also because I have accumulated a whole bunch of different calculators over the years, and it is the easiest way for me to quickly figure this out. So you're probably more familiar with your calculator, so you can probably use something different, but I personally use fractional exponents. But there's a couple different ways to use cube roots on your calculator. You get to figure it out. So that's what it is at pH 7. So now what I want to do is now I want to basically do the exact same problem, but I want to do it at my pH of 9. So in order to do that, I'm going to basically rewrite my reaction. So I still have my magnesium, I still have my 2 hydroxide, but we were using my pH equals 9. So at a pH of 9, I should know what my hydroxide concentration is. So I still don't care about my solid. I still have none of this, but this is changed. I know I have hydroxide. So I would really like hydroxide. There are a couple of different ways to solve for hydroxide from here. I'm going to go ahead and use that 14 minus to get POH. Gives me 5. So 5 is equal to my POH. So 10 to the negative 5 is equal to my hydroxide concentration. I did skip a few steps in there. So in case you're curious, the steps I skipped was from 5 equals POH. This is also 5 is equal to the negative log of my hydroxide concentration, which means negative 5 is equal to the log of my hydroxide concentration, which means that 10 to the negative 5 is equal to my hydroxide concentration. Doing this 10 to the negative is essentially 10 to the negative is just part of the formula. Using the 10 to the whatever it is essentially how I get out of the logarithm. Also, for any of you that are either studying mathematics or are more acquainted with logarithms, you have my sincere apologies for the language and terminology that I just used. But since in chemistry, we don't test you on what the wording is of dealing with logarithms, I just use words that I hope will help like undo the logarithm. I do have friends who are mathematicians. They don't like it when I say that. They roll their eyes at me. So for the record, I know that that's not the right language, but it works for the purposes of this. Yeah, so that's what I'm dealing with. So therefore, I'm going to take 10 to the negative 5, and that gives me the hydroxide concentration. So my hydroxide concentration is 1 times 10 to the negative 5. So therefore, I'm not starting with 0. I'm starting with 1 times 10 to the negative 5. I still am going to add x. I still add 2x here. X 1 times 10 to the negative 5 and 2x. Now, I'm going to make an assumption here. And to be honest, this might be an oversimplification. I don't think it is. Because I have that 5.6 times 10 to the negative 12th. This x is still going to be really, really small. I am still going to use the x is small approximation. So when I do that, I get to assume that this x is 0. So therefore, what I'm going to assume is that this is still x, this is still 1 times 10 to the negative 5, but then I'm basically taking 2 times 0. So I am assuming that I still get to use the x is small approximation in my mathematics. This whole thing is still squared though. Don't forget to do that. So I am just assuming that the concentration of hydroxide given is the amount of hydroxide that I'm using. So I am basically ignoring that plus 2x, but I'm not ignoring the squared term. So then, as I do this, this is not going how I wanted it to go. Regardless, I'm just going to finish my calculation. and pretend that this is still working. This did not work though. I have some thoughts about why it didn't work. Mostly, I bet I have to actually deal with that squared term. Every once in a while I do something that doesn't work. Darn it. We'd have to use a larger pH. Darn. So the reason why I don't like this is because I'm not getting the answer I wanted, which is now when I divide this, I get something like 5 times 10 to the negative 2 is equal to x, and that looks like it's more soluble, which means I did something wrong. So I am really sorry about this, y'all. Something is wrong. I think what's wrong is this assumption that I made is wrong. But on an exam review, I am not going to, I basically would need to go back and rewrite my problem, because if I can't use the x to small approximation, then this problem doesn't work for the exam. It's too complicated. So that would have worked had I prepared that in advance, but I didn't, and I was trying to be helpful in showing off how to do calculations with exponents, and it bit me. So something's wrong. That should not happen. Something's wrong. I'm going to assume that we needed to rework the problem. So the math part's fine, aside from the concept not working out the way I wanted it to. But the steps themselves are valid, including, honestly, the fact that on an exam, we would expect you to use the x is small approximation should you be faced with this. It's just the comparison didn't work. That's really the only thing that failed me, is my comparison. Well, that's too bad. But we did at least talk about the common ion effect, and KSP, the letter S, which sounded just like the letter F. So we did actually talk about that. Percent ionization and then buffer capacity. And let's not solve for percent ionization. Let's put percent ionization in the problem. I'm going to make this larger in just a moment. And we want the percent ionization to be kind of high, because essentially the x is small approximation should not work. 7.9%? Sound good to you? Okay, and now making it larger so you guys can actually read what I wrote. Dun, da, 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 boom. An unknown acid has a percent ionization of 7.9%. What's the Ka value if the initial concentration is 0.5 molar? So this is a percent ionization problem. You're given a percent ionization problem. You're actually asked for the Ka value in this case. So we're going to look at how to solve this problem. So first of all, what's percent ionization? I'm going to go ahead and grab the potentially useful information page, because there is a percent ionization formula on here. And so we're going to look at it. Sorry for that very loud sound. That was my screenshot sound, because I don't really want to copy the entire potentially useful information. I just want this. So this is percent ionization. It says the amount ionized divided by the total amount times 100. So we need to finesse this definition just a little bit, because the amount ionized is really going to be the change, and the total amount is really going to be my initial concentration. I'm going to show you a conceptual version. I'm going to show you a picture version of this. So usually when I'm talking about percent ionization, here's my solution, and I have molecules of weak acid. I realize that it looks like the solution is laughing at you, but it's not. And then when we have this in equilibrium, I expect some of these to be ionized. So here is one ionized, and here are all of the other ones. So what I would do for here is I want the amount ionized. So that's one ionized molecule out of the total amount. Well, the total amount was 1, 2, 3, 4. So the amount ionized is 1, the total is 4. I can then multiply that times 100 to give me 25%. So 1/4 of all of them, 25% ionized. So I usually like to demonstrate that with a picture just because the formula's wording is correct. The amount ionized divided by the total. The wording is correct, but it's very easy to make this more complicated. But all we're really trying to ask is out of all that you started with, how many of them ionized? So my total is really just the initial. The amount that ionized is what in an ICE table we would refer to as the change. So that's really what we're looking for, is the change. So when we rephrase this, I can use my ICE table relatively easily to figure out all the different pieces that I need. So I'm going to have my percent ionization, which is that, what did I say it was, 7.9%? And that's going to be equal to my change divided by my initial concentration times 100. So I'm going to divide by 100. 0.079 is equal to my change, that's X, divided by my initial concentration. That's why there was an initial concentration in the problem. We have to have that. 0.54 molar. So I grabbed my initial concentration, 0.54 molar. I then am going to solve for my change. So my X is 0.04266. I want that because the question asked for my Ka value. So I'm going to think about all the parts that a Ka value has. So I'm dealing with this thing, 0.5400, and my Ka value has to be at equilibrium. My Ka value has to be at equilibrium. Now, here's the other thing. I know what the X is. Y'all get so used to using the X as small approximation, but the X is not small here. The X is small approximation. Also, you don't know that because we're supposed to use the Ka value to figure out if X is small. Also, you have X, so there's basically no excuse. No approximations if you have percent ionization. You do not get to use approximations if you have percent ionization. If you have percent ionization, do not use the approximation method. Don't do it. Because you'll get the wrong answer and you'll be sad. 2 divided by 0.54 minus 0.0. Sorry, I'm on basically my backup calculator. I don't know about y'all, but I have this thing with both like pens and pencils, and unfortunately, now that I have them calculators, where they're just they're kind of in equilibrium in between like home and work and my bag. And that means that sometimes all of them are at home, and sometimes that means all of them are in my bag, and sometimes that means all of them are at work. But that definitely means that sometimes I don't have what I need. There's my Ka value. So percent ionization, a lot of that is knowing that it really is the change divided by the initial concentration. The formula that's given is still correct, but it uses different language. So being familiar with percent ionization is mostly to be familiar with how to use it, and that you're going to include it. No approximation when you're calculating your Ka value. No approximation. Okay. I know I haven't answered all the questions, especially because I came with a bunch of questions. So I haven't talked about buffer capacity yet, but are there any questions from the chat?
Yes, you have one more new question.
Okay.
Can you do a problem where we find the gram solubility?
Oh, sure. Absolutely. Which one do I want to do? Let's go ahead and do buffer capacity first. So, because we're getting kind of close to time, and buffer capacity is really not that bad. So buffer capacity. So first of all, whenever you say buffer, there's two different things when we talk about buffers. One of them is buffer range, and one of them is buffer capacity. So first of all, the question that you did not ask, and I recognize you didn't ask it, is buffer range. Buffer range is that idea that you're looking for a pH that is plus or minus 1 pKa unit, or pKa plus or minus 1. So when we talk about the buffer range, you're basically asking over what pH can this thing be a good buffer? And the buffer is good where you have roughly equal amounts, and we're usually okay with equal amounts to about 10 times more of one than the other, which is where the plus or minus 1 comes from. So buffer range is where if you over what pH range is my buffer valid, and that's the pKa of the buffer plus or minus 1. So that's buffer range, not the question that was asked. Buffer capacity. So whenever we talk about the word capacity, this has connotations in the English language. So you might actually see like an occupation, or like a, not occupation, sorry, like a room capacity or an elevator capacity. Elevators usually is in weight. It'll tell you how many pounds the elevator can handle. That is actually useful not for hauling people, but for hauling luggage or for hauling like physical items. So if you, because usually if you're going to move furniture, you usually move furniture in the elevator, right? You don't move furniture in the stairwell. And some furniture is really heavy. And it's good to know what the capacity of the elevator is. You do room capacity, how many human beings fit in a room. Sometimes you see that as occupancy instead. Sometimes you see it as capacity, how many people fit there. Buffer capacity, therefore, is essentially how much strong acid base can the buffer handle. And this is based on the concentration or the number of moles of the buffer. So for example, if I have just two buffers, I've got 0.001 moles of ammonia with 0.001 moles of the ammonium ion compared to 1 mole of ammonia and 1 mole of the ammonium ion. they're both buffers. They'll actually also, because they're equal amounts, they'll both give you the same pH. But one of these has a higher buffer capacity. B has the higher buffer capacity because I could put in 0.5 moles of HCl and I would still have kind of the same pH that I started with. It would change. Adding an acid to a buffer does change the pH, but I would still have a buffer if I added half of a mole of hydrochloric acid to B. If I add 0.5 moles of HCl, I don't have a buffer anymore on A. No more buffer. I would have reacted away all of the buffer. I would have exceeded my buffer capacity. So buffer capacity is just all about how many moles of the buffer do you have, and therefore what's actually present. So how much strong acid or strong base could it handle? So that's buffer capacity. I'm looking at the time and we've got about 3 minutes left and I cannot do that grams calculation in 3 minutes. It takes too long. So I'm actually gonna scroll back up real quick and see if there's anything else out of the list from my class that I can potentially hit real quick. So, and really what I'm gonna do is I'm gonna make their list real big for a minute. All of them need to be big, not just some of them. Okay. So a couple things from my class. How to use log or window to subtract to pH, subtract 14. So we did talk a little bit about this as the review was going on. The main game is to keep track of proton versus hydroxide and pH versus pOH, because essentially the negative log of your proton concentration will give you pH, but the negative log of your hydroxide concentration gives you pOH. So I know that those are very similar to each other, but that's what you're trying to keep track of, is what do you have and what do you need. You can also use that potentially useful information page because those two formulas are actually on that potentially useful information page to help you keep track. So if the question asks about pH, that is different from pOH. But you can move in between those with that 14. So that's what the highlighted one was the fact that you can move in between pH and pOH by the number 14, because we say pKw, which is correct, but it's really the number 14 because we're going to be at 25. We're going to assume we're at 25 degrees Celsius for all of these. Do you have any tricks on how to memorize strong acids and strong bases as well as solubility rules? So I gave my class the solubility rules, but you don't actually need those. Solubility rules, you're just going to look for KSP values. And KSP will tell you that there's something that you need to calculate. So my trick for memorizing solubility rules is don't. Just use the KSP values. Don't bother memorizing solubility rules. How to memorize strong acids and strong bases. I usually go with a periodic table as you can. I know it doesn't cover all of them. Flashcards also help. Difference between titrations. I think we made a flowchart for this. So I think that I answered that question as well. BCA or ice tables, I think we answered this question as well. So BCA is when you have a strong species. whether that's a strong acid or a strong base, that's when you're going to use a BCA table. And it is now 5 o'clock. So you can see that there's still questions from my class that I didn't get to answer yet. So I will be making a follow-up video. That follow-up video will also have a solubility problem where we're looking for grams as well. Was there anything else new out of the chat before we log off?
Yes, you have one more question of can you do a buffer problem where you add either an acid or a base?
Absolutely. Can do. Okay, that's it. Is that it? That was a question. Question mark, is that all?
That is all the questions that we have in our chat today.
All right, fantastic. Then it is 5 o'clock. We covered a lot of stuff, but we'll go ahead and log off. Good luck on the exam. You can do it. Good luck.
Thank you so much, Dr. Taylor, for presenting for our study session today. Our next study session will be held on April 28th for the next exam. So for all of y'all in here, we would love to see you guys then. Otherwise, hope you have a good rest of your evening. Okay, everybody? Take care and peace out.